Yesterday we learned how the area under a curve could actually be computed using the limit of the sum, like we have here. Definition of an area, so it's as many rectangles as possible, all added up, their height times their bases, which makes sense. We have yet to actually calculate those, and we still won't be doing that today, but what we will be doing is just talking about what this actually means. So, if f is a continuous function defined for a is less than or equal to x is less than or equal to b, we divide the interval into n subintervals of equal width, just like we talked about yesterday. That finds us the width of the rectangles because it takes the whole width, divides by the number of rectangles. We let a sub 0 equal a and so on be the endpoints of these subintervals, and we choose those staple points where the rectangles divide, and we end up with this notation. Well, what you didn't know is that that notation is an integral. So the integral, which is what that symbol means, from a to b of f of x dx, is equivalent to those formulas that we set up yesterday. The symbol integral was introduced by Leibniz and is called an integral sign. It's an elongated s, and the reason it's an s is because of it is the limit of sum. So sum starts with s, that's why they picked s. In the notation, what's inside our integral is called the integrand. So there's a couple vocab words for you: integral sign, integrand. A and b, also some new words, are called the limits of integration. A is the lower limit and b is the upper limit. Typically, in an integral, the lower number will be at the bottom. Not always. We'll get to that later. The symbol dx indicates the change in x, or the change in x, and will be substituted for the width of the rectangles. On an integral, the width is so small we represent it with a dx, but we don't actually have to put a value there. We'll talk about it more in the next few lessons. What we're really doing today is we're going to be estimating still using LRAMs and RRAMs and MRAMs, but they're not called LRAMs, RRAMs, and MRAMs anymore. They're actually called Riemann sums. And that's the process of calculating the area by approximating rectangles. So this is a Riemann sum because it uses some set number of rectangles, base times height, and adds them up. This yellow area is the integral because it is the exact area under the curve. That makes it an integral. One change for today, when you're doing your rectangles like these two pictures up here show, any rectangles that are below the x-axis will be negative area. Remember to draw those rectangles from the curve just to the x-axis. Stop at the x-axis. So these rectangles are positive, but these are below the curve, so they're considered negative area. You will actually have positive area and negative area that cancel each other out. You could essentially find an area and get a value of 0, which is mind-boggling because how can area be 0 if you can see area? But that's calculus for you. So you'll see why as we get deeper into these integrals. So, express the following as an integral. They didn't plug in x sub I, so it looks like our function is this. And that our change in x, remember, gets substituted by dx. Lower limit is 0, upper limit pi, so this is actually the integral from 0 to pi of x cubed plus x sine of x dx. So not real tricky to change from summation notation to integral notation, but is something you should be able to do. But today you will be approximating with rectangles again. Keep in mind, any rectangles below the x-axis are considered a negative area. All that. I don't know what this means, but change in x is dx. So, if you have questions, we can talk about those tomorrow.